It's a pleasure to introduce Rahim Moosa from Waterloo University. Rahim earned his PhD from the University of Illinois Urbana-Champaign. Following that, he had appointments at Berkeley, the Fields Institute, and MIT until he joined Waterloo in 2004. Currently, he's a professor and holds a math faculty research chair at Waterloo. Rahim also served as vice president of the CMS and as editor for the Canadian Journal of Mathematics and the Canadian Mathematical Bulletin. He's also the founder and editor-in-chief of the journal called Model Theory. He's a world-leading expert on model theory and implication, and he'll speak today about recent applications of model theory to algebraic dynamics.
Actually, it's very nice to be here. I was just saying, I've only been here a couple of times. It's nice to be back. I'm talking mostly about some joint work with Moshe Kamensky. I've been here in Bullion. And this is about, as a subset, applications of model theory, which is a branch of mathematical logic, to algebraic dynamics, which is subject in algebraic geometry. And so, unfortunately, I think this means I will not likely be able to say much about either subject. But I will try to begin by at least articulating the theorem in algebraic dynamics, a theorem in algebraic dynamics that proved. So the application, I'll focus on just being able to state it. And then what, of course, I'd like to have done is to give some idea of the approach, the proof method, which comes from logic. This will be a little bit difficult to do, but what I'll try to do at the second half of the talk is just say something about why, how model theory intervenes, why should logic intervene. So everything I'll talk about in the beginning will be algebraic geometry, dynamics, why should logic have anything to say about this. So that latter part might be a little bit soft. I won't get to details. So the theorem is in algebraic dynamics. And really, what I mean by this is the objects that I'm really interested in looking in studying here are rational dynamical systems. Which I might abbreviate as S. And so, what is a rational dynamical system? It's a pair where V is some algebraic variety. I should say I'm working entirely. So let's fix an algebraic enclosed field. K of characteristics zero. But you can take a complex field if you like. So I have an algebraic variety over K. And what is phi? It's a dominant rational self-map. So I write it as a map, but it's not actually a function everywhere. We have poles. It's given by rational functions, so it may not be defined everywhere, but it's defined on some Zariski open set. Maybe to fix ideas, I don't know how much in the way of algebraic geometry prerequisites I should cover, but yeah, so what kind of varieties? I'm thinking about, say, quasi-projective varieties here, but if you like, you can concentrate with affine varieties, so cut out by polynomial equations and affine n space and n variables, systems of equations. But maybe to fix ideas, it's worth considering what is already sufficiently, a lot of the complications already arise. So you can consider the case when the variety is affine n space itself. Right? So it's all of affine n space. Okay. And then, what does it mean to have a dominant rational map? You just fix rational functions, say n rational functions in, say, n variables over your field, which are algebraically independent of a k. And you take phi from affine n space to itself to be given by, so A is a tuple of an n tuple of elements, and you just evaluate these functions, these rational. So that's the fact, the dominance, the fact that the image is, yeah, so dominant here means that the image is Zariski dense. And that comes from the assumption of. So this is, for example, a rational map. It's not defined everywhere because these rational functions, denominators are poles, some places where they're not defined. And this is already exhibits most of the kinds of things that we're talking about. I should say you could work there. I mean, it's already interesting. The main case is when, say, phi is an automorphism, so it's actually a regular map. There's no indeterminacy locus, and is in fact an automorphism. The reason I don't restrict my attention to regular maps or automorphism that work in this slightly more general category is not because to be more general, but because the notions about this that I'm thinking about are up to birational aspects. I'm really not going to be able to say much about the sort of global structure of the variety in this, this endomorphism of it, this automorphism, say, in that case. For example, what's happening on some small Zariski closed subset. I'm only going to be able to say things about what's happening generically, what's happening on the Zariski open set. So the right setting is where I work in this level. So one is interested then in such pairs, algebraic, right? Why dynamical system? Well, because if you think of the case where it is defined everywhere, then it's there's a self map, so there's some dynamics. Look at the orbits of points, you study things like points that are fixed or periodic. And particularly think about invariant subvarieties. That's going to be our main focus. So if those are the main objects, what are the sub-objects? So an invariant subvariety of a rational dynamical system is an irreducible subvariety. Sorry, these varieties are all irreducible. Is an irreducible subvariety, say X, V, where phi maps X to itself. So such that phi of X that's back in X. Now, because I'm not assuming that phi is regular, this includes the assumption that X intersects the domain of phi trivially. And then by the image, I really mean the image of that where it's defined. And I also want to ask that it's Zariski dense. It's containing that it's n Zariski dense. It is. Yeah, so it's really a sub-object. Yeah, so the point is that it follows that if you look at X and you look at phi restricted to X, and this is also a rational. It's a sub-rational. So those are the invariant subvarieties. Now, I'm not actually, I already said that I'm only really able to talk about what's happening generically on variety, on Zariski open sets. So somehow, by definition, I can't really say anything about invariant subvarieties because they don't happen generically. They're nowhere dense closed subsets. But so what I'd really be looking at are the invariant subvarieties in Cartesian powers. So I want to associate to this rational dynamical system the invariant subvarieties of its powers. Yeah, so note that phi acts also on e to the m for an m 1 diagonal, coordinate-wise. Yeah, I mean that. Yeah, a field acting from V to V, so it also takes V to the M to V to the M, where it acts on each of the V coordinates. And so I also again I'll denote this by V to the M with phi. So this is also right. So for each, when I start with rational number system, I get a rational number system on every Cartesian power. I don't put phi to the n here because that could be confused with iterating phi, which is of course something also to be interested in doing when you have a dynamic system. So I just use phi itself in the context to say whether I'm acting with V or on Cartesian power. And I want to look at invariant subvarieties. Interesting. Invariant subvarieties of all these Cartesian powers. But those that when you project onto any one V, they project surjectively, or at least dominantly. So that it really is, tells us something about on a Zariski open subset of V itself. The subvariety is which project dominantly, so has Zariski dense image onto each V coordinate. Yes. Subvarieties V to the M that are invariant on the diagonal action of phi, and which project on. Because such a thing is then giving us some relationship between a large part of V, Zariski open subset of V, and its powers. An algebraic relationship that is compatible with the dynamical structure. So what's really behind this is just a basic classification problem up to birational equivalence, birational isomorphism of such pairs. And the approach is that we can understand a lot about this rational dynamical system by understanding all of these invariant subgroups. Yes?
Maybe you're going to, but is there a sort of motivating example of this kind of invariant subvariety of a power that means something conceptual beyond just polynomials?
Yes. You mean where it's rational rather than regular? You mean specifically about rational examples versus polynomial examples?
Either would be fine.
Well, so I will give some very specific examples, and I think they will largely be polynomial examples. But you can see from here, you just choose any algebraically independent rational things you get examples. So there's this is very broad category. There are lots of objects in it. But I will give some examples. Let me actually just give right away a trivial example, maybe turbulent. So here, I mean, what if phi is just the identity? There's no, the dynamics is just the identity. Then all subvarieties of V or powers of V are invariant because it says nothing. And of course, there are many of these. So in this case, what am I looking at? I don't have any dynamics. I just have an algebraic variety, and the subvarieties of its powers, well, those that project dominantly on each other. And so then I'm just doing sort of pure algebraic geometry. And so the way to think of this is it's an expansion of algebra. There's the algebraic variety, but then there's this additional structure called dynamics. And I'm interested in the sub-objects of powers in the expanded thing, right? So because there's more structure, the sub-objects have to preserve that structure. Right? So the invariant, so there'll be fewer invariant subobjects because there's more structure. Fewer. But if I work in the case where the dynamics is trivial, then there's no additional constraint, and I'm just looking at all objects. And of course, I'm not going to say anything about this. Really, it's about the general case, maybe how it relates to this, how far away it is from the pure algebraic geometric situation. And so in some sense, it's a kind of, when I say the classification problem, the way I said it, it would include birational classification of algebraic. It's not something I'm talking about, but rather, relative to the pure algebraic geometric case. What new objects arise? How different are they from pure algebraic geometric case? Okay, but I'll give specific examples in a second. Right. Okay. So actually what I'm interested in, as I say, is in somehow the opposite case, where there are very few invariants. And how can that happen? Okay, so this is maybe step 2. what I call disintegration. Terminology is motivated from the model theory point of view, but I don't think it's a bad name. So let me say what I mean here. So possibly there are no invariants. So that can't literally be true. There are always some, right? So there are always some invariants. Proper. There's for the whole space, but proper invariants of varieties. B itself is yours, and my subvarieties are always invariants. Somehow important, right? If you're looking for points in field, it is. So, for example, the diagonal in B squared. Right? So it's a pairs that are A equals B. That's a proper subvariety, projects dominantly, it's clearly invariant, whatever phi is, because phi is acting diagonally, so it serves the diagonal. So you're always going to have these, so you can't expect not to have these, but you also have things like the graph of phi. Yeah, so the set of all pairs A phi of K. So here maybe I'm sort of assuming that phi is defined everywhere, otherwise you take this risky closure of this. And this is also in B squared. It's also invariant, right? Because if I apply phi coordinate-wise, I land back in the graph because phi commutes with itself. And it will also project. So these exist. And also iterates. Similarly, for iterates. Iterate phi and take the graph of phi squared. So now by phi squared, I mean you apply phi twice. And that will also give me. So I have these basic invariant, proper invariant subvarieties projecting down. They always exist. I've done this in B squared, but they exist all M in various things. I call these kinds of things phi diagonals. So maybe I'll write it down. So the question of there being no invariant subvarieties is really the question of none except these, the ones that always come for free. And so let me give the definition. Let's fix some M bigger than or equal to 2. And we say that a rational dynamical system is M disintegrated. Exactly what I said verbally. If the only proper invariant subvarieties of B to the M disintegrated refers to a particular Cartesian power, are the phi diagonals. I guess I mean subvarieties defined by equations of the form some I coordinate, so I'm writing AI for the ith coordinate of the M is equal to phi raised to some power applied to some other coordinate. So different coordinates. So those are the phi diagonals. They're in V2, I was talking about here. In VM, I cannot talk about these phi diagonals. So fine, not just one equation, maybe several different coordinates related by inputs. Phi, so this is some. It's 0, including diagonals themselves, yeah.
So you don't care about the fixed points or anything like this because those don't project dominance.
That's right. That's right. So yeah, so it's not about fixed points, it's about sort of fixed subproblems. Okay, so that's what I would mean by disintegration. So it's somehow a totally different situation than the trivial dynamics, where some examples. So trivial dynamics are not M disintegrated. Oh, maybe I should first of all observe. Let's just note that. Also, that's what M disintegrated means, and then we say B phi is totally disintegrated. If it's M disintegrated for all that. this would be the extreme case where you have no interesting invariant subvarieties in any particular class. Okay, so let's look at a few examples to get a better sense of this notation. All simple examples. I'm not going to work out any complicated ones. So I've already talked about make sure I do want to go examples, yeah. So I've already talked about trivial dynamics. Yeah, I was going to note, maybe I'll put it here. Note, if M is less than or equal to R, then R disintegrated implies M disintegrated. It's not hard to see, right? So this condition of being M disintegrated, as you take larger M, becomes a stronger condition. So if you had some invariant subvarieties, interesting invariant subvariety in M space, and you can just take the whole thing, that will give you an invariant subvariety in R space. These become stronger conditions, and totally disintegrated is when all of these conditions, stronger, all true. So trivial dynamics is already not too disintegrated. Yeah, so it's not. Maybe these are non-examples. It's not too disintegrated because, well, everything is invariant. So you're really just asking, this is an algebraic geometric question now. There's no invariance. It's just subvarieties of E squared. And algebraic geometry is never disintegrated for many subvarieties. I say, I'm assuming the dimension of these positive. So self-correspondences, although there's continuous families of self-correspondences of various degrees. Think of, for example, where P is just the affine line, and then I'm talking about, curves given by polynomial in two variables, and lots of polynomials with higher and higher degree, and these will all give me. So you won't get, it's very rich. Algebraic geometry is too rich to have this integration. So these guys already at the level 2 fail. Let's look at another example. Let's take the affine line, and let's take the dynamics, which is the square. So this is not trivial. There is something. Not everything is invariant, but there are invariant subvarieties. So this is also not too disintegrated. So, for example, you could take the graph of the cube. Yeah, this is invariant under this action. Because if I square both coordinates, I land back and get x squared x to 6 back. It projects onto both things, proper sum. So things like this would happen. So it doesn't happen in trivial dynamics because algebraic geometry is not disintegrated. Why isn't it happening here? What's really going on is that this is a dynamics on a group. It's a group dynamics. This is a group endomorphism. Monomial maps like this are group endomorphisms of the multiplicative. I mean, I wrote A1 here. If you throw away 0, this is the multiplicative group equipped with an endomorphism. And that's what's giving rise to these examples. In fact, it comes from
or it commutes with something that's not a power itself.
Sorry?
This map commutes with something that isn't a power itself. That's your.
Yeah. Right. Exactly. Why you get something that's not a phi diagonal? It also commutes with power. So not yeah. So I should have pointed that out. Yeah. So in the trivial case, the phi diagonals are just actual diagonals. But here there are phi diagonals, but there are also things that are not phi diagonals. They're not powers of x squared. Things like this, and you can imagine other examples like this. Let me talk a little bit more about the following example, or a class of examples called translational. Translational dynamics. Which is a special class of dynamical systems that sort of, if I understand correctly, by the way, I'm not myself an algebraic dynamics person, so to some extent looking from the outside. So, but these are dynamics that are well understood and are very well obtained behavior. They're somehow the easy case in many of the open questions in algebraic dynamics, translational dynamics. You see that it's true. And what are they? They also come from an algebraic group, but not where an endomorphism on an algebraic group, but rather where the phi, the dynamics, is the phi is part of an algebraic group action. So there's a whole algebraic group of dynamics, of which phi is one element. Yeah, so there's a. This is the case where there is an algebraic group action. Say G acting on B, so there's an algebraic group action G of B, and phi is an element of that group. So it lives as part of an algebraic group action. So I want them to be over K, so this is equal. These guys are also not two. And maybe it's somewhat illustrative to give the short proof of this. They're also not two. So let's sketch why that's the case. Well, first of all, so phi is now an element of a group. There's a whole group action. One. Maybe phi is a finite order inside this group. So in that case, if phi is a finite order, let me just say one reduces to the case of trivial dynamics. Example A, after some power, phi becomes the identity. So maybe phi itself is not trivial, but some iterative phi is trivial, and then the non-two disintegratedness of phi to the power n can be pulled back to a non-two disintegrated. There's something to do here, but this is the relatively easy case. So we may assume phi is of infinite order in G, right? So when I talk about the order, I mean as an element of this group. Its iterates is just group multiplication in G. This is part of a group action. So what happens in that case? Well, in that case, consider the cyclic subgroup of G generated by. Maybe you can see already from this point of view about finding things other than its powers that it commutes with. That's the key here. So you look at cyclic subgroup generated by phi, and you take its Zariski closure. Let's call that. This is Zariski closure. So this is now an algebraic subgroup. And it's commutative. Because the cyclic subgroup is a commutative group, right? Cyclic groups are commutative. And when you take Zariski closure, coming to the D is inherent. So this is a commutative algebraic group in its own right, it's a subgroup of G. And because phi was of infinite order, this is a positive dimension. And if you have a positive dimensional subgroup, it can't be equal to the cyclic subgroup. So there must be something in here that's not a power. Exists like H in H that's not in the group generated. It's not an integer power. So here, by the way, phi is an automorphism. If you have groups act by permutation, these are all phi in this case is an automorphism. Each element of the group gives me an automorphism phi. And I can look at negative powers as well. And I take something that's in H, so it's in the Zariski closure, but it's not one of these. It's an algebraic subgroup, an algebraic group of dimension even one cannot look like this. In this sort of discrete counter. I guess I want it to be in H. So that's also. And now consider the graph of this H. Which is a subgroup. So H acts on V. It's an element of G, so it's an automorphism of V. So its graph is a subvariant of V squared. And it's invariant because of the commuting method. Invariant as H commutes with V. Because that's a commutative group. And it's not a phi diagonal precisely because it's not a power. And it's proper and it projects onto it. Gives me some. So a lot of examples that you can come up with, if you look at the affine line, say with translation or something, they come from an algebraic convection. The additive group acting on affine space by translation, for example. All of those not two. So that's a whole thought. So these are all not two something. Let's look. The question is this. What about examples that are disintegrated? Well, I'll just write one down. Not very hard to write down, but it's hard to prove. It's a known example, so this is D. So take the affine line again, and just perturb example B a little bit. So instead of taking x squared, take it to x squared plus in some sense, you're combining an example from C and an example. This guy is totally acceptable. Not so easy to see. This was proved, say, by Chatzidakis-Hrushovski in the 90s. Though maybe it was known. I mean, they give a proof in the paper in the 90s, and it's really a sort of a complicated difference algebra. It's a real algebraic argument. There's not really much model theory in the proof. It's really we can give an elementary proof, but a complicated one. But in any powers here, the only things you can get are feet. Why? In fact, what's the case, despite all of these examples, is that, and maybe you guessed this, that if you write down a random dynamical system, that would be the expectation. It's complicated, it should be very hard to preserve. There would be some varieties that are preserved for usage. So this should somehow be the typical case. So when you start writing down specific examples, and the one is not important for anything other than 0, I think -2. Yeah. Okay. So, okay. Now, in these examples, which is not supposed to be exhaustive in any way or to illustrate it, it's just very particular examples. I guess here there's sort of class examples. There's certainly a gap, and you can ask, okay, not 2 disintegrated, totally disintegrated. What about in between? Are there things that are m disintegrated but not m-1 disintegrated? And now I can state at least a theorem, something that comes out of our application. This is actually just 2 weeks ago. And it's a 3 disintegration. Implies total. So the gap here is not just because of my very special choices of examples, but there really is a gap. So if you have a rational dynamical system and you want to know if it's totally disintegrated, now why you might want to know this? I mean, so this is connected. Maybe I say something about where this comes from, like why we were trying for this for quite some time. It really comes from the situation with algebraic differential equations. So the analog of dynamics being algebraic vector fields. So instead of dynamical systems, think about rational vector fields, where the map is not a self map, but a map to the tangent, section to the tangent. You can make you talk about invariant subvarieties, you can make very similar things. And there, talking about disintegration, total disintegration in that context means that you have some algebraic differential equation, and you look at solutions of these equation in some field of functions, and total disintegration is saying that there are no algebraic relations between solutions. A common thing to do in algebraic differential equations is, for one thing, is to study particular solutions and their analytic properties or something. But another thing to do is to try to understand what the algebraic relations between solutions are. And this is somehow an extreme case. It's a very strong property that there are no algebraic solutions. That translates precisely to this total disintegration. And this is an analog of that for what are called difference equations, which I'll talk about later. So these rational dynamic systems are sort of the geometric counterpart to difference equations as opposed to differential equations. And I could state this in terms of difference equations, precisely the same kind of statement. So particular examples of total disintegration tend to be hard, like this example here. And there are others that people work out, and it takes work in their different methods for specific examples, similarly with the differential case. And we were looking for some way of simplifying understanding of when this happens. And we were able to show this in the differential case maybe 3 years ago, and since then have been working to understand the difference case. And I should say, this is the sort of culminating paper. There's a series of 3. It starts actually with some work with Jason Bell and Matt Satriano, colleagues at Waterloo. That's purely in algebraic dynamics, does not use any logic. Maybe in 2023, and then something we did last year, which did other things, but both of those papers are used. Results there are used. So I'm not sure how well I've motivated it, but anyway, that's the statement. You only have to check in free space that there are nothing other than phi diagrams. You get that they're never.
Would that make somehow that there or we check for free?
Yes. I mean, not hugely easier, but definitely. And okay, so it's a question of applying this to other examples. We haven't really got there. We definitely expect other interesting difference equations that arise, different interesting rational dynamical systems that arise that one expects to be totally disintegrated. This should be so. Now, you should notice that the examples are not too disintegrated, so I don't know if this is sharp. Question. Still open to us, which is there? I mean, this is something that the algebraic dynamics people who work with particular dynamics might have already know, but I haven't been able to find. Is there a two disintegrated rational dynamical system that is not three disintegrated? In other words, can this actually work with you really just have to check two? We think not. We think this is sharp. We have constraints. We kind of know what an example should look like, but we have not yet managed to actually get that case remains. We think is there? We think yes, which make this short. Two disintegration is not enough to get to this. But that's the statement. I don't know if there are any questions, and I can move to the theory. Some discussion on logic is involved. Yes.
How do you practically find invariant subvarieties with this B cross B cross? Is there a bounding degree? How far would you look to assert yes, there's no more beyond certain points?
So by beyond a certain point, you mean
in degrees. So you've given me and I want to check that it's not threes.
Right.
It's,
in order to see that,
yes.
so check that it is threes.
Yes.
But they're not. Well, yeah, it's not. Those techniques will still have to be specific to the particular. We don't have a general way of checking this. So the whole question started by, can we have a general way to check this? And in some sense, this is an answer. General ways to check. In particular examples, it is often if you're bounding, if you're working with a fixed space, it is, as one might expect, much more kind of tractable, but it will be specific to. But yeah, so this doesn't help you answer this part. It tells you that's all you need.
How much of this story works in positive characteristic?
That's a good question. I'm not so sure. So various bits of this paper are in general characteristic, and there's some intermediate theorems that are. But in the end, we use some very particular techniques from model theory that have to do with, I guess they'll come up in the second part, that have to do with the connection with the fixed field in a difference. So you have some field with an automorphism of the field, and you're looking at the fixed points, and it's the sort of model theory relationship to the fixed points. And in positive characteristic, that's not enough, because there are, so the main point is that in positive characteristic, there are algebraic automorphisms of fields, namely for Beams. And so you have to look at the fixed fields that are compositions of your given automorphism with powers of the Frobenius, positive integer powers of the Frobenius. And so we just don't have the model theoretic machinery, just isn't quite there. So a lot of our ingredients come from Chatzidakis-Hrushovski, and they do have there's another paper where it's joined with, in addition to these two, with Pisazel that works positive characteristics, but it's extremely common. So there are a few places where we use sort of deep, for lack of a better word, theorems from model theory that we only know in characteristics.
would you expect the answers to be the same even if you don't know the groups go through, or could it be possibly different?
So for this statement, so this is like a particular, I sort of extracted a particular statement that I could easily describe. I don't know if I've thought about whether this, the theorems that give us this, we do expect to. Of course, you have to include either phi diagonals for being so there should be a natural generalization of phi diagonals because those will also always exist. But I think the answer is yes, that we would expect that generalizing phi diagonals appropriately take into account the Frobenius maps. Which maybe shouldn't be true if your variety is not. So I guess what we'd expect is that it should be true if the variety has what do you call this? FP trace 0. So it's defined over some function field, but not defined over FP power, and not the image of something defined over FP. So very much not defined over finite field. Oh yeah, there's a good question. Okay, let me try to say something in the remaining time about why logic intervenes. Or model theory in particular. So why model theory? And this will say a little bit about difference equations and so on. So really, it's the process is from the geometry to the algebra, and then from the algebra to so if you start by the geometry, I mean your actual dynamic system, you can associate to this an algebraic object under the usual algebraic geometric correspondence. So the variety corresponds to an algebra function, right? So the general correspondence is between geometric spaces, the function, algebra is a function of the space. So you would look at functions of the space, and our rational setting means the natural algebraic object to look at is a function. So this is a finitely generated field extension. Okay? So that's what the variety gives you. What does phi give you? It gives you a map, phi star, which is an endomorphism of this field. Right? I don't know if this how much explanation I need. I mean, what do I do if I take a rational function of v? I should view it as a map from v, say, to the affine line, if you like, and then I have phi, which is a self map on v, and so I get another map to the affine line, and that's my phi star. So f goes to precomposed, right? So first to phi, and that gives me. The fact that the map was dominant ensures that this is a non-trivial, this is a non-zero. An injected map from the field to itself. The K endomorphism preserves K, and it's an injected. And that's what we mean by difference field. So a difference field is an algebraic object. It's just a field equipped with an endomorphism. I'm working in characteristic 0, but this makes sense in general. A field F equipped with an endomorphism, often an automorphism. For example, if this was a birational map, but in general, and a non-zero injected map, endomorphism sigma. So what I get out of the rational dynamical system is a difference field. That's algebraic dynamical. And I can go the other way, right? If I start, maybe I just do this verbally. I guess I have, what do I have? So, 5 minutes or something?
Oh, 30. 30, right?
Yeah, okay. I won't do that. I'll just say, yeah, sure. I thought it was 50 minutes. But, I go the other way, right? I mean, if I start with a finitely generated extension of K, so maybe I just said it, every finitely generated field extension F of K equipped with an endomorphism, sigma is of the form F is going to be the function field of some variety, and sigma is going to be phi star for some dominant. That's what I mean by going the other way. So in algebraic geometry, that's already clear, right? I mean, function fields are finally generated field extensions are called function fields because they are function fields of varieties, right? So there is some variety. So basically, you choose generators, fix some choice. So there's some choice because there's an embedding issue. But let's say fix generators for f, n of them. Then I can view f as the function field of some affine subvariety of n space, because I can view f as the fraction field of the polynomial ring of invariables modulo primary. And then the endomorphism of f will be given by rational functions. And so we go the other way. So this is actually so we go. So we have correspondence between well, I'll just write E of E star. This difference field in these rational dynamical systems, and it's a correspondence that completely captures the birational structure, right? That's the birational geometry of V is completely captured by its rational function field, and the birational geometry of the dynamical system is completely captured by this. So to study rational dynamical systems up to birational isomorphism is precisely to study these algebraic functions. In some sense, it makes this an algebraic problem. It doesn't really help, it actually hurts, but in many ways, but because it's complicated, difference fields are complicated, but we get this. The advantage for us is that once you have a class of algebraic objects, it's natural to axiomatize them. So logic behaves much better in algebra than geometry. Now, we know this when we teach algebra classes, right? It's in some sense easier, right? You write down the axioms for groups, and then there's some geometry you have to convey some actual ideas there. So here you get rid of the ideas that you can draw. This is the wrong direction. That's not what I did. Okay, so you can try to axiomatize this. So we can axiomatize difference fields. Now we can't axiomatize finitely generated fields. So axiomatize, I mean in first order logic. I'm not going to explain all this, but say in the formal language. In the formal language, where you give yourself the symbols for fields, plus and times, and you give yourself a symbol for the difference fields, right? So I'm talking about difference fields, f sigma, and I can write down the axiom saying that f is a field and sigma is an endomorphism. I can write them in a finite tree way in an explicit, well-defined list of axioms, which we do for fields all the time. We'll imagine how to do it for sigma. We cannot axiomatize, the only ones that show up here are function fields. We can't axiomatize that for a variety of reasons. I mean, how many generators, right? In first order way, if you fix the number of generators, maybe you could say something. But even then, generating in how many steps to actually axiomatize it. So you'd have to really look at very specific. In there, you'd have to restrict to n generated in m steps or something to try to axiomatize. You can't axiomatize all finite. This is sort of standard compactness. So I have to kind of give up on finally generated, and they have to show up some other way later. But at least I can axiomatize difference fields. So I can talk about difference fields. Now, in model theory, just because I can axiomatize it, that's not enough to do model theory. I mean, you can axiomatize anything in algebra, but not all objects have a good model theory in the sense that the model theory, studying those axioms gives you much information. What you want is to really study the geometry of the difference fields, the geometry of the rational dynamical systems, but the geometry associated to this algebras is you want some kind of closed difference. So if you forget about the dynamics and just think about fields and varieties, so varieties and function fields, that's the algebra geometry correspondence. It's not enough when you're studying algebraic geometry to what am I trying to say? To witness the geometry of the variety, you have to look in algebraic closed. You have to look at the points in algebraic. The points in a given field won't exhibit all of the geometry, might have no points and so on. They need to be closed. And that has a general model theoretic parallel. Namely, so what we are interested in what's called existentially closed difference fields. And this existentially closed difference fields relate to difference fields in exactly the same way that algebraically closed fields relate to fields. And you can talk about existentially closed structures in an arbitrary logic. This is not specific about fields. You do this in a very general setting. But what does it mean to be an existentially closed difference field? It's a difference field F sigma such that any system, finite system of difference polynomial equations and inequations. Right? So what is a difference polynomial? It's a polynomial not just in the variable x when finding many variables x, y, xn, but also sigma applied. Just like an algebraic differential equation is like a polynomial equation in the variables and its derivatives. So this is a polynomial equation in the variable and its transforms under sigma. So any system of different polynomial equations and inequations which has a chance of being solved, and I would say the way to describe that, be consistent, is that it should have some solution in some extension, which can be solved. So a system of equations which can be solved in some difference field extension. Of F sigma is already solved in F sigma. And so that's the key note algebraically of being existentially closed. So these things always exist for general nonsense reasons, right? If it's not, you start with a difference field as non-existentially closed, then you have some system of equations and equations. It has a solution in some extension, so look at that extension. Now, if it's not difference closed, you know, you can enumerate all the systems of equations and equations, and maybe some sort of transfinite reduction to unions or limits or something. It's totally general nonsense. You can always embed a difference field into an existentially closed difference field. You can always close up. They're not like concrete objects, and in fact, in pure algebra, they're also. I mean, I guess algebraic closed fields feel more concrete because we have. We think of C as a concrete algebraic closed complex numbers as concrete algebra. But really, the construction is just some kind of abstraction. So these always exist. That's no problem. The problem is, why can I axiomatize them? The essentially closed difference fields are not necessarily axiomatizable. This, what I've written down is a definition, but I can't axiomatize this in first-order logic because it talks about extensions. Yeah, so I'm allowed infinitely many axioms. So for each system of equations and equations, I can have one axiom. But what do I need to say about the system? I need to say it as a solution somewhere else. But in first-order logic, you can only talk about the structure. Your quantifiers, your variables, they vary among the elements of your structure. So it's not an intrinsic property with some kind of extrinsic thing. So the question is this axiomatizable, first-order axiomatizable? And that's really what Chatzidakis-Hrushovski. So thanks. That's that. Hrushovski showed that existentially closed, I'll just say EC, difference fields are axiomatizable. I won't say what the axioms are. It's enough for the model theorists that they are axiomatized. There is an axiomatization of class space. And whenever you have that, doing the model theory of that theory, so this gives rise, in theory, the set of first-order logic, which goes by the name ACFA, 0, it's the characters 0, which now doing model theory of this theory should tell us a lot about difference fields in general. And then in particular about finally generated difference fields, and then something about rational dynamics. So this is how it intervenes. Go from the rational dynamical system to these finally generated difference fields, to the class of all difference fields, to existentially closed difference fields, and then apply the model theory here. Of course, that's where all the work is. This theory is turns out to be relatively ill theory. So the techniques of model theory arising in the 70s, Zilber and Shalon and Hrushovski and others, apply to this theory. And you can use the model theoretic tools and prove logical theorems, model theoretic theorems about this theory, which you then can extract. This theorem.
Where is the number 3?
You mean where? Yeah, it's not here. Why is 3 the right thing? That's theorem is right. Why 3 is the situation that's needed. It does come down to finding groups. Yeah, so you from a general situation where there don't seem to be any groups around, you reduce yourself to where there is a group action. And once you have a group, you have x, y, x plus y, which is a ternary invariant relation, which when you don't have, so when you were 3 disintegrated, you can't have any groups. And there are no groups around somehow. So it's the absence of groups. Now not quite there, like on the nose, it's the series of reductions, and then it's related to a group problem itself. And when you do this, it's actually, because it's a group action, it's really more like 4, because it's a torsor. So you have a point, and then you identify with the group. So it's really 4, and then you have to work hard to get down to 3. Like if it was a group itself, then 3 would be the right number, just because the group operation is a ternary, the graph of the group operation is a ternary relation. Yeah, so maybe that I think.
Follow up.
Yeah.
So do you have a result from the small theory side of things that we need to do the 3 each chart?
No. We think it's because so I said that it was motivated by a similar theorem that we proved in 2022, other authors in the differential case, and there 2 is the point. So in some sense we started believing it should be 2 in all the model theory 2, but again it's a hard work. So 4 you can get from some point, and then maybe some work to 3, and then we thought maybe some more work to 2. But in trying to prove the case of 2, we realized that there's a certain amount of leeway in the different situation in algebraic dynamics that you don't have in dynamical systems that you don't have in vector fields. It should allow it. So it's more specifically about algebraic dynamics than it's a thing that's pretty much sharp. But it's really, we didn't succeed. We tried. So it could vary. It really could vary. It's not like we're sure it's just that's how it's.
What kind of stability properties does this theory have? Like stable?
No, so actually, so that's a complication. For people, so this is for people who know about some model theory. There's a hierarchy of tameness that questions referring to, stable and megastable, different ranks. This is not even stable. It's a simple theory. Simple in the technical sense, which is more general than stable, less simple than stable in some sense, more complicated. But so it does have that. That's a hierarchy. It's a super simple theory, but it's not stable, which is why the differential case is super stable, mega stable, and so that was really why it didn't. The same arguments didn't quite work. What we had to do, see, if you look at this theory, if the non-logicians will bear with me for a second, it doesn't have quantified language. So, and that's a huge obstacle. But the things we're interested in, the rational dynamical systems, they're all from algebraic geometry, so they're all quantifier free definable. So how we do this is we restrict attention to the quantifier free fragment of this theory. So we only look at quantifier free definable sets, quantifier free types, and we take that machinery I was talking about of Shalar and Zilber and Hrushovski, and we show that it works just with the quantifier free fragment, and then apply it to the quantifier. So we really have a stability theoretic proof. So it doesn't have quantifier limitation, but if you look at the quantifier free fragment, it is in some sense quantifier free stable. Quantifier free fragment of this theory behaves like an omega stable theory. So we have to adapt.
And there's a stupid question. What does FA stand for at the end? I guess AC is that pretty close.
Oh yeah, so it's a terrible acronym, so I don't like to say what it is. It's just what it is, but I'll say it. It just means algebraically closed field with an automorphism. But it's totally not that. Like those aren't the axioms. You can't just say that. Yeah, so it's it should be, automorphism. It should be maybe generic automorphism, or you could say difference closed field or something. But it's not just an algebraic closed field. The axioms are much more sophisticated. It's only in the 90s, for example, that the axioms were written down. But that's what it said.
Is it complete?
It's not complete. That's another complication. That's a good question. That complication we don't deal with. The way I swept that on the rug is I said start with K algebraically closed. The completions of this theory, once you know the characteristic, are what the automorphism, how the automorphism behaves on Q bar. Once you know how the automorphisms are, different automorphisms that you restrict, you get automorphisms that balance with the absolute Galois group. Every element of the absolute Galois group gives you the full completion. But I started with K in the algebraic closed field, everything was over K, so sigma is the identity of K. So my sigma on the algorithm, the absolute algorithm is the identity. So that fixes the condition. And really, these theorems you'd want, so this assumption that I'm working with algebraic closed field is a weakness in the statement. You'd want it to be uniform in completion, which corresponds to just asking to be working with some field. And I'm sure that, like, for example, the arithmetic dynamics would much prefer that it didn't work over that. Just a Q. But then there are different completions to work. And there are theorems about proving things uniform. We assume that Q bar is in the fixed field, and that gives me a condition.
No.
Any other questions?
More than one math? Aha. Yeah, so that's very good question. So if you take, for example, so then we did yes, they find in various particular contexts. One issue is what if you have two maps? So let me talk about the algebraic setting. So you have difference fields with two automorphisms or endomorphisms. If you don't ask that they commute, then we do get a axiomatization of the existential closed constructs. If you ask that they commute, so you only look at the class that commutes. So notice in the definition of existential closed, you talk about an extension. So it's relative to the class. So I'm working here in difference fields. So if I was working in difference fields with two endomorphisms, which I insist commute, then it becomes a very different problem. And it's known not to be axiomatizable. So Hrushovski has proof that pairs of commuting automorphisms is a non-axiomatizable. The theory of pairs of commuting endomorphisms is axiomatizable, but the theory of their existentially closed structures is not. So it kind of depends on that kind of thing. So that's one way that it's studied. So people have looked at non-commute where you don't ask that they commute, and then it's a little bit wild. With more natural things that commuting is. There's no hope. Okay, there are ways around without axiomatizing the stage closed field, but they're complicated. So you can't really say much. The other aspect of multiple things that people looked at is finite groups of elements. So one is like the group Z. They're looking at a grid, so we're just looking at Z acting on field. Let's just take the case where it's an automorphism. I'm looking at Z acting on field. Two is like Z squared if they're commuting, but free group of two generators if they're not commuting. But what if you take just finite groups acting? That also has some dynamical content, but it's more like finite order dynamics. But there is we call this a model companion. Existential closed models have maximization, say things. Yeah. So those are the two directions I know of.